Yeah, thank you very much. I want to start by thanking Serguei and Natasha for organizing this very nice conference again, and to be able to participate in this very nice meeting. I will discuss in this talk non-thermal electronic phases, ordered phases in photoexcited or otherwise perturbed Mott insulators. And this is work done in collaboration with Martin Eckstein in Hamburg, Yuta Murakami, who was here last week, Chia-Chun Lee, Markus Müller, and Andreas Leuchli at the Paul Scherrer Institute, and Tsu-Chei Ray, my current postdoc in Fribourg. And yeah, basically, as a motivation, let me just mention that unconventional superconductivity or other interesting quantum phases appear in the vicinity of Mott insulating phases. For example, in the cuprates, we know that superconductivity appears if we chemically dope antiferromagnetic Mott state. Also in the fullerite compounds, there's a superconducting dome next to Mott insulating phase, and also in the kappa organic compounds, superconductivity appears next to a Mott phase. So these are, by the way, all the three material classes where light-induced superconductivity was claimed to be found by the Cavalieri group, but I don't want to go into this. Rather, I want to ask the obvious question. So if we can find interesting quantum phases by metallizing a Mott insulator in one way or another, can we also find interesting electronically ordered phases by photoexciting charge carriers across a Mott gap and producing some non-equilibrium state? And that's quite a reasonable proposition, because if the Mott gap is large enough, the photocarriers can be long-lived. And then basically we have, in a single band case, we have doubly occupied and empty sites which act as charge carriers. And if the system is coupled to some environment, some bosonic modes, phonons, or other bosonic excitations, we can imagine that these charge carriers lose their kinetic energy and they cool down within the Hubbard bands, but without recombining. And then we end up in a metastable state, which has effectively called non-thermal charge carriers, doublons and holons, and this might lead to some interesting new phases, for example, a condensation of these doublons and holons into a superconducting state. And so in this talk, I want to very briefly discuss three different types of strategies for inducing non-thermal orders in Mott systems. One is a simple idea: if we have intertwined or twined orders in a system, we can try to selectively melt one of the orders and then realize some kind of new combination of orders that are not achievable in equilibrium. The second strategy I call entropy trapping. This means that we have some strong constraints on the dynamics, which enables the emergence of new types of orders. And the third is the activation of new particles like these doublons and holons in Mott insulators. They have new types of interactions which can then lead to interesting quantum states. So let's start with the selective melting of orders in a system with intertwined orders. Here I will show results for a 3/4 filled 2-orbital Hubbard model. That's work done by Chia-Chun Lee in Martin Eckstein's group at the time. So we consider this system on a cubic lattice, and there is an interesting ordering pattern in equilibrium. Namely, we have fully antiferro orbital order, while the spin order is ferromagnetic in the XY plane and antiferromagnetic in the Z direction. So that's the equilibrium state. And now we may ask, how does this state react to temperature and to photoexcitation? So I do illustrate this by plotting the two order parameters in this two-dimensional plane. So horizontal axis is orbital order, and the vertical axis is magnetic order. We start in in an equilibrium state with this type of combination of orders, and then if we heat up the system in equilibrium, then somehow the thermal excitation of spin waves very quickly melts the spin order, and we kind of end up in a state which has only orbital order. So under heating, the spin order is kind of more quickly melted than the orbital order. The solid lines here, they show what happens under photodoping if we photoexcite charge carriers that cross the gap and introduce these non-thermal charge carriers in the system. Then what we see is that the orbital order melts more quickly than the spin order, and we can realize states which have kind of large spin order but strongly suppressed orbital order, which are not achievable under equilibrium conditions. And we can kind of understand this by just reminding ourselves that the antiferro order is very fragile against photodoping. And I illustrate this with these arrows. So these arrows in this case would correspond to the pseudospins for the orbital pseudospins. But anyhow, this mechanism works for all type of antiferro orders. We have an antiferro background. We inject a hole or a doublon into this background. This hole moves in this antiferro background, and with each hopping, it flips this arrow against the antiferromagnetic background, and that very quickly then leads to these so-called string states, which easily then disorder this antiferromagnetic background. And that's what's happening in this simulation. Because the antiferro order is, because the orbital order is fully antiferro type, it is very easily destroyed by these string states, whereas the spin order, which is ferromagnetic in the planes, is robust against the diffusion of these charge carriers, and that's why only the motion in the z direction can disorder the spin pattern, and that's why in the non-thermal case the spin order is in this system much more robust than the orbital order, and that's why we can reach these non-thermal combination of orders. So that can be, I think, a general strategy for inducing, basically ordering patterns which are not achievable in equilibrium. Then the second example I want to briefly discuss is an entropy trapping related ordering. Here I also consider a two-orbital Hubbard model, but this time a Hall-filled two-orbital Hubbard model, which has a crystal field splitting between the two orbitals, and we have a Hund coupling in this system. So if we just look at the atomic problem, there are basically two types of states for small crystal field splitting. Compared to the Hund coupling, we have three spin triplet states. So we have locally large entropy of log 3, whereas if the splitting of the levels is large compared to the Hund coupling, we have only one relevant state with both electrons in the lower orbital, and so we have a local entropy of 0. And somewhere in between there's a spin state transition. And that remains in the lattice environment. If we simulate now a lattice problem, what we find is basically a transition from a low spin insulator to a high spin insulator at a certain level of the crystal field splitting. And what Jan Kunesh showed several years back is that the lattice system in the vicinity of this spin state transition is unstable to excitonic order. The order parameter is written here. It's a kind of spontaneous formation of an interorbital hybridization, or we can also view it as an electron-hole type condensation. So that's a phenomenon very closely related to superconductivity, and here in this case it is a spin triplet type of order parameter. Now what we did in this study is we started in the low spin state, and we quenched the crystal field splitting into the region where excitonic order exists at low temperature. So we could imagine that this is done by nonlinear phononics or some other way. Let's just assume we can quench the crystal field splitting in our system. And then the interesting thing is that even if we start at high temperature initially, above the highest excitonic insulator temperature, we can, after this quench, break the symmetry. And here you see the evolution of the order parameter. And after many kind of oscillations, it will thermalize in a symmetry broken state. And what is happening here is that as we kind of quench to the right here in this, say, phase diagram, we start to form high spin states. These have a large entropy, so there's a flow of entropy from the electronic sector to the spin sector, and that cools down the electrons, and that allows us to break the symmetry into this excitonic phase. Now, even more interesting was the finding that if we quench beyond the regime where excitonic order exists in equilibrium, we can still break the symmetry. But now you can already see from the trajectory of the order parameter in the complex plane that this is now a very different type of symmetry breaking than in the red case. And yeah, a closer analysis of the problem showed that this symmetry breaking is related to entropy trapping, which means that because of the strongly correlated nature of the system, the low entropy of the initial state is approximately conserved under the time evolution, and this very strongly constrains the dynamics of the system and allows this type of symmetry breaking to happen. And just to illustrate how unusual this is, let me try to illustrate these two scenarios with some free energy landscape. So in the red case, we have the usual symmetry breaking where the free energy potential changes from parabolic to Mexican hat-like, and then the ball rolls down into the new minimum and oscillates around the new minimum. These are these amplitude or Higgs oscillations, which you see in the red curve. The blue one is very unusual. Here, the potential does not qualitatively change. The minimum remains at zero, but still, in the non-equilibrium state, we can break the symmetry and the order parameter starts to roll around this parabolic-like potential, and we get, at least transiently, a symmetry broken state with a large order parameter. I want to very briefly comment on possible relation to an experiment by the Shimano group. They have recently revisited these light-induced superconducting states in the cuprates, and they have shown that these light-induced superconducting states have no Higgs modes. So that rules out this type of symmetry breaking, because here we would have Higgs modes in the system, but it does not actually rule out this type of unconventional symmetry breaking where we would not expect any Higgs mode. So yeah, there are two possibilities. Either this state is not superconducting, that's maybe the most likely possibility, but if it is a light-induced superconducting state, we will probably have this type of unconventional symmetry breaking to at least metastable superconducting state. Now, in the last minutes, let me switch to the third scenario for inducing non-thermal phases. That's the activation of new types of particles like doublons and holons. And here let me start with a paper by Achim Roche from several years ago. They considered the strongly repulsive Hubbard model, which has only doublons and holons, so that's a very high energy state of this model. And they argued or showed with mean field type calculations that this system can become superconducting with a staggered order parameter. So the usual equilibrium system, say in the attractive Hubbard model, would have a S-wave superconducting solution which has the same order parameter on each lattice site, but this non-thermal superconductor in the repulsive Hubbard model, this has a staggered order parameter where the order parameter changes sign between the two sublattices, and I will call this type of superconductor a eta pairing state. Now, a few years back, Kaneko and co-workers, they studied a one-dimensional Hubbard model with strong repulsion, and they showed that by applying a a clever laser pulse, they can basically induce a state which is reminiscent of this eta pairing state. Namely, this blue line shows the pair-pair correlations in the chain. In the equilibrium state, you can see it decays very fast. These correlations decay very fast in equilibrium, but then after this laser pulse, they start to form these staggered correlations, which are almost not decaying. So that's very suggestive of the induction of this eta pairing state. And also with dynamical mean field techniques, we were able to stabilize this state. For example, one can use the so-called steady state dynamical mean field formalism, where one couples a fermion bath, a full bath, to the upper Hubbard band to produce some doublons, and the empty fermion bath to the lower Hubbard band to produce some holes. And by tuning the coupling strengths and the temperatures of these baths, we can to some extent control the density of these charge carriers and also the temperature, effective temperature of these charge carriers. And then one can map out a phase diagram in the space of photodoping concentration and effective temperature. And what this shows is that this eta pairing phase is actually very stable as a function of photodoping. It does not only exist in the fully photodoped limit, which was discussed by Roche and co-workers, but it extends down to low photodoping concentrations. And more recently, Yuta Murakami used another technique, so-called effective equilibrium approach, to study this problem. And with this, one can really kind of simulate the effective zero temperature state of these photodoped systems. And he showed that in this effective zero temperature state, eta pairing is actually stable almost down to zero photodoping. So in the equilibrium state, we have antiferromagnetic order, but then as soon as we introduce these charge carriers, we get the eta pairing state as the effective ground state of this photodoped system. Now, eta pairing is naturally stabilized on a bipartite lattice, but one may ask what happens on a geometrically frustrated lattice, like a triangular lattice. In particular, one can ask, can something analogous to the 120-degree spin order be realized in a photodoped superconducting system? And that's indeed the case. What we find with DMFT is that on such a lattice, we have a superconducting state which has a 120-degree phase twist between the green, blue, and red sublattice. And because of this phase twist, there are persistent currents running around these triangles, and they break time reversal symmetry. So this photo-induced superconductor on the triangular lattice is actually a chiral superconductor, a very rare example of a chiral superconducting state. And that could be experimentally detected because it has very characteristic responses to external fields. If we apply, for example, an electric field pulse in the vertical direction, it would induce a supercurrent response transverse to this field, and that would be a very characteristic signature which one could look for in an experiment. Yeah, this is another kind of exact diagonalization calculation which suggests that indeed these kind of correlations for the 120-degree condensate become very strong beyond a certain photodoping fraction of about 0.33. So that's consistent with the DMFT results. Now, the triangular lattice Hubbard model has been studied a lot in connection with these kappa organic compounds. And as I mentioned in the Cavalieri group, they also found superconductivity, light-induced superconductivity in this bromide compound, and there was some speculation in the paper that maybe this is a eta pairing superconducting state. I think that's not very likely because this kappa bromide compound is actually metallic, so we don't have long-lived doublons and holons in this material, and that's really needed for this eta pairing scenario. Also, we would rather expect this 120-degree order and then eta pairing, but yeah, maybe it would be interesting to revisit this with the chloride cousin of this material, because this copper chloride compound. This is actually a Mott insulator at ambient pressure, and so it would be very interesting to try to photodope this copper chloride compound and then search for maybe eta pairing or 120-degree type condensates in this material. Now, in the last minutes, I want to switch to multi-orbital systems. Already in equilibrium, multi-orbital Mott systems have very interesting phase diagrams with different types of electronic orders. This is a two-orbital Hubbard model in the space of filling and interaction strength. So here's half filling, here's quarter filling. Near half filling, we find an antiferromagnetic phase. Away from half filling at strong interaction, a ferromagnetic phase. And in between, an orbital singlet spin triplet superconducting phase. And this is a particle Hall symmetric model. So on the electron doped side, we would have the same phase diagram. And now we can ask ourselves, can we start in the half-filled state and then by photodoping singlon, triplon type of excitations in the system generate a non-thermal version of this spin triplet superconducting state. And I tried this already several years ago. I applied a laser pulse to the system and measured the order parameter for spin triplet pairing. And indeed, the susceptibility goes up after the laser pulse, but not very much. So this was not enough to claim that there is a symmetry breaking in the system. But at that time, we didn't understand yet that in these laser-induced condensates, we have to look for staggered ordering rather than uniform ordering. So more recently, then I asked my postdoc Suche to revisit this problem and look for the staggered version of the spin triplet ordering. And indeed, he managed then using this steady state non-equilibrium formalism to produce a Mott insulator which has very strong photodoping and very cold effective temperature. And then indeed he finds a spin triplet pairing of the staggered types, eta type spin triplet pairing for very strong photodoping. So that can also be realized. And then most recently we have then studied a system where we have two different bandwidths, so a wide band and a narrow band. And then we find a very rich and interesting non-equilibrium phase diagram. So basically, this is the photodoping concentration. The vertical axis is the ratio of the bandwidth. In equilibrium, we start from an antiferromagnetic insulating state. If we have the same bandwidth, we get this spin triplet eta pairing state at very strong doping. But now if we break the symmetry between these two bands, then we find a very robust light-induced ferromagnetic phase, which is stabilized by the kinetic energy of the photocarriers. We find a coexistence of light-induced ferromagnetism with spin singlet superconductivity, and we also find a region where only spin singlet superconductivity of the eta pairing type appears. So this is maybe the most rich non-equilibrium phase diagram which we have found so far, and that's just for a very simple two-orbital Hubbard system. So that gives us kind of confidence that by studying even more complicated systems, we can easily realize more interesting non-equilibrium electronically ordered states. And with this, I'm done, and I just flashed the summary. I briefly surveyed these three different strategies for inducing non-thermal phases: selective melting of order, entropy trapping, and the activation of new degrees of freedom. And with this, I stop and thank you for your attention.